Hello everyone. In this video, I want to cover a little bit more on our normal distribution and how these convert into what's called our standard normal. Okay, so when we've done our normal distribution so far, we've kind of just mapped out our distribution, we've drawn out our midline, which is our mu, and we've said that to the inflection point right here is equivalent to one standard deviation. And then we've been labeling it such as, let's say that our mean is something like 120 and the standard deviation is equal to 20. And then we've been able to relabel our graph in terms of numbers of standard deviations away from the mean. So we go up like 3 and we go down 3, and then we can label this as like 140, 160, 180, and then going the other direction, 100, 80, and 60. Okay, so we've done this so far, and we've used kind of our z-score equation to tell us how many standard deviations away from the mean is our observation. So we've done this x minus mu and divide by the standard deviation sigma. And so we've played around with these things, and we've also started to deal with, remember, our empirical rules, where we know that plus or minus one standard deviation away from the mean captures 68% of the data, plus or minus two standard deviations was a total of 95% of the data, and then plus or minus three standard deviations has 99.7% of our data. Okay, and those were our empirical rules. So let's talk a little bit more about what we were actually doing here. So when we do this and when we kind of calculate out our z values, this is called standardization. Just write that up real quick. Because if we remember when we talked about our normal distributions, if something follows the normal distribution, as soon as we have it defined, as we know what our mean and our standard deviation is, we know that these empirical rules hold. And in fact, what we are doing is we are really taking our individual scenarios with the individual mean and the individual standard deviation, and we are converting it into this standardized normal distribution, or what we could also call like a unit standard deviation. So let me draw out what's called like a standard normal distribution. So same shape and everything, except when we standardize, we call this a mean of 0 and a standard deviation of sigma equaling 1. That way, each step away is this plus or minus one standard deviation, plus or minus two standard deviations. This is our standard normal. So this is going to be -1 for -1 standard deviations, -2 standard deviations, -3 standard deviations, and over here this is +1, +2, and over here is +3. So whenever we use this equation right here, this z equation, when we are converting our mean and our standard deviation and our observation into a z-score, we are converting from a specific normal distribution to our standardized normal distribution. So whenever you hear something that's called standardization of our distributions, we are converting our specific standard deviation scenario into one where we have the mean as 0, and each standard deviation step is just literally 1, and then to 2, and then to 3. That's called standardization. Now, the reason why we might want to standardize, and we'll go into this a little bit more, is because instead of just using the empirical rules, where we were able to find some things, we could find, for example, the area from -2 standard deviations to like +1 standard deviation. Like we could do that. That wasn't hard. We could figure out it was that like 68% plus 95 minus 68 divided by 2, and we could add those together, and we found that it's like 81% for that. Well, what happens if we want to do something a little bit more specific? Let's say that I want to go from like a half standard deviation to like just a little over 2. Like if I wanted to do something like this. Now, I could use my empirical rules to try to figure this out, but it would be off because the empirical rules, like really, we only do these by the steps. They're actually rounded as is. They're just kind of these like basic guidelines. And the question is like, well, what could I do here? Well, historically, what we did is we then took what we called these standardization, and we got a z-table. And a z-table would tell us from very different spots along here from the number of standard deviations, what's the area from a specific point and below. Now, when we do this like area under the curve, let me kind of erase this out. When we talk about area under the curve, we really are talking about things like calculus, where we are trying to take the integral of something, and we're trying to find like the area from a point and the area all below. We could do this with integration. However, how the normal distribution is developed, you actually can't take a direct integral of it. You actually have to use like approximation techniques. And so in order to facilitate this, early on we built tables. We built what were called like z-tables. And these z-tables went up incrementally, so starts from like -3 and goes all the way to like +3, and it would take very small steps, like 3.01 and then 3.02 and then 3.03, all the way up from this range from -3 to +3, and it would tell us what the area is from a specific point and all the way to the left. What's nice though now is that we have software that can help us tell us the exact area between any 2 points on this graph. So we can look at, maybe we're interested, let's suppose that this is like how much money somebody makes in tips on a weekend, something like that. So 120 normally distributed with a $20 standard deviation. Maybe we really want to know like what's the probability of making between like 125 and 175, and that's what we want to know. We can do that using our Excel tools, but it all comes down to this idea of standardization, figuring out some sort of z-score. And so let's say that we were looking for between, let's write this down, between let's do